Hello, a very warm welcome to another instalment of our YLP webinars brought to you by the Young Leaders Program of the International Desalination Association. The YLP is a program set up through the International Desalination Association which aims to promote desalination as a career choice amongst young professionals and provide education such as these webinars and opportunities such as our mentorship program and further career advancement. And today we're very pleased to have Dr. Mohammed Wakil Shahzad, a research scientist at the King Abdullah University of Science and Technology and a fellow committee member of the Young Leaders Program. Dr. Wakil has vast experience in the field of desalination and field of heat and mass transfer, having written 40 journal papers, 13 book chapters, published 1 book, as well as holding 7 international patents. And more specifically, Dr. Wakil has been working on the hybrid desalination processes such as the innovative MED plus AD process or combination multi-effect distillation with absorption desalination process, which looks to optimize the advantages of both these processes and provide the lowest overall treatment cost to desalinated water. And following on from this work in the field of energy efficiency and energy transfer models, he's here today to present his webinar, The Fallacy of Energy Efficiency for Combined Desalination Processes, where he examines the way we currently view energy efficiency for desalination and not only challenges these perceptions, but goes one step further by proposing new assessment criteria. Before I hand over, just a little reminder that if you have any questions, you can ask them at any time by simply adding the questions to the comment stream that's available on our live stream on YouTube. And that will allow me to pose them to Wakil at the end of the presentation. So if you have any questions, please enter them as soon as you have them. Without further ado, I'm very pleased to introduce and hand over to you, Dr. Mohammed Wakil Shahzad, for what is, I'm sure, to be a very interesting presentation. Over to you.
Thank you very much. Hello, everyone. I am Mohammed Wakil, as Nick introduced. I'm working as a research scientist in a water desalination and reuse center here in KAUST, King Abdullah University, Saudi Arabia. And today I will be presenting about energy fallacy of desalination process. And actually, it's a very interesting topic and also very important and timely. So, I will just start my presentation. Energy fallacy, the fallacy of energy efficiency for desalination process comparison is very important. And the reason behind this work was that the different processes are used to desalinate the seawater. But the important is that how we can compare all the process to make sure that all the processes are at the common platform to show the energy efficiency of all the process to compare with each other. So this was the main idea behind this work. And but before going to all this detail, I will just go through the global and the GCC water scenario, that what is a water scenario, and then the desalination process comparison, what are the desalination process and how we can compare all the process, and then what is our standard primary energy concept. That is actually a main idea in the presentation. And then the standard universal performance ratio that we introduced for the first time to compare all the desalination process at a common platform. And then I will also show that the future sustainability roadmap, that what technologies can be sustainable for future seawater production. And after conclusion, I will go through our innovative cycle, that how we move from the industry, from the lab to the industry, and how we successfully installed our pilot, and how we are going to install our first plant at Jammu, Saudi Arabia. So in terms of water availability and demand, we can see over here that the water withdrawal in 2010 and 2030, and it's around 4,500 to 7,000 billion cubic meter. And it is estimated that there will be a deficit of 40% between availability and demand by 2030. And what are the reasons behind this? The availability and the demand is actually majorly the world population. So we can see over here very clearly that in developed countries, the population increase is not so much, but in the developing countries, the population increase is very high. And because of this reason, we can see over here that in the developing countries, specifically in the Asian region, the water consumption is very high. And the one of the reason is the population increase in this area, and the secondly, the GDP growth rate. And due to this, the excessive water withdrawal, we can see that the most of the countries now under water stress region. So what I mean by the water stress, any country where the water availability is less than 1000 cubic meter per capita per year is called water stress country by the United UN standards. So in terms of the water stress, we can see that all the red zone is actually under the water stress area, and we can see the most of the countries are actually now under water stress. And if we zoom into the GCC countries, where the situation is even worse, and we can see that the most of the GCC countries, the water availability is less than even 500 per cubic meter per capita per year. So this situation is very severe in GCC countries. The reason is because almost there is no rainfall, and the groundwater is also mostly is used for the agriculture purposes. And what are the reasons for this the water shortfall? We can see that the major reason is the poor agriculture practices, because more than 70% of the water is actually utilized for the agriculture purposes. And the second reason is inadequate infrastructure. So most of the time, the countries where there's enough rainfall, sometimes they cannot capture the water properly, and it actually goes to the sea or some other areas where it cannot be reused. And it can be a policy constraints, some of the degradation of the water quality, increase of the water demand because of the GDP growth rate, and it can be a policies. But over here we'll not discuss about the policies, but we will discuss the other the problems. Those are actually the major reason for the water shortfall. So what can be the solution for this water shortfall? So one solution can be the wastewater recovery. We know that the industrial water use is quite high, and we can actually recover the wastewater, and then we can reuse it after treatment. And the secondly, we can teach the people to use the water wisely, because we know even in the morning, if you leave the tap open and during the brush, it lost around 20 liter water. So we can teach the people to use the water wisely. And the third, it can be we can harvest the water. It can be surface water or the rainwater. But even we do all these practices, we can see that it can only fulfill 40% of the 40% gap that will be available in 2030. So still there is a 60% gap that cannot be fulfilled, even we apply all these practices. So the only solution for this 60% gap is a seawater desalination. There is no other solution to fulfill this 60% gap in 2030 to fulfill the demand of the water in all the countries. So only the seawater desalination can fill this gap between the availability and the demand that will be in 2030. So the seawater desalination is not new. It's already installed. 19,000 over 19,000 plants are installed in 150 countries. Those are producing 38 billion cubic meter per year, and it is projected to increase around 54 billion by 2030. And we can see it's installed in the Gulf countries, and on the seawater desalination. So in term of the feed water, we can see the majorly over 67% the process are based on seawater desalination, and more than 60% desalination capacities are installed in the GCC countries. And the reason is because, of course, as I showed, that the GCC countries are highly water stressed countries in all around the world. If we compare to the other countries of the world, because of the very low rainfall, almost there is no rainfall. And in terms of the desalination process, we can see the majorly is two process. Those are commercially installed in the industry. One is a thermal methods and the other is a membrane methods. There are some other methods, those are not very successful in the industry. And out of these thermal and the membrane, in thermal, the multi-stage flashing and multi-effect desalination process are very famous in the industry. And in terms of membrane, the reverse osmosis is installed at the large scales. In terms of installation, if we look into the installation, we can see in the world, RO process are dominating with 53%. The reason is because in the world, mostly the process are installed on the breakage water. So the RO is good for the breakage water. But in GCC countries, where there's almost mostly the installations are on seawater, the thermal process actually cover the highest market, that is more than 60%, because the thermal process are very reliable with the condition of the Arabian Gulf. So that's why the RO process are not very, you can say the dominating, but the thermal process are very much dominating in the GCC countries. But the important is either it's a RO process or the thermal process, there is a nexus between water, energy, and environment. So we cannot just take one process and we can apply it. Actually, any process that is applied to the commercial scale, it need to fulfill this nexus for the sustainability. So we have to produce water, but we have to apply some process that actually consume very less energy, and also we have to help to protect the environment in terms of CO2 emission and the brine rejection. So we have to develop and introduce some process that actually fulfill this water, energy, environment nexus. But unfortunately, today we can see process, all the conventional process, they consume a lot of energy. They are very energy, like not energy efficient. So around 75 terawatt hour electricity is consumed by the desalination process throughout the world per year. And they emit around 76 million ton of CO2. And of course, they are sharing a very big portion to the environmental issues. So we have to look for the process that fulfill water, energy, and environment nexus uh, to achieve COP21 goals. So now the question is, as I mentioned, that the two processes are very commonly employed in the industry. One is a reverse osmosis and the other is a thermal process. So which process is efficient? So in terms of reverse osmosis, there are a lot of publications are available in good journals in water, in Journal of Membrane Science, in desalination, energy, and in science and environmental sciences. And there are many reports, and all they claim that RO processes are very efficient. But on the other hand, the thermal group is also working very hard, and they also have the publication in similar level of the journals like environmental science, energy, and in some nature publications, and renewable and sustainable energy reviews. And they also claim that all the processes are very efficient. So now the question is that which process is efficient? How to examine the process efficiency. So if we look into the process energy consumption, we can see over here that typically the RO process, they consume electricity 3.5 to 3.8 kilowatt hour per cubic meter. But the thermal desalination process, they consume electricity as well as the thermal energy. So in terms of MED, they consume around 1.5 kilowatt hour electric per cubic meter and around 60 or 61 kilowatt hour thermal energy per cubic meter. And MSF energy consumption is a bit high because the temperature, operation temperature is a bit high. So electricity is around 2.5 and the thermal is around 72 kilowatt hour per cubic meter. So now the question is whether we can guess from here that which process is more efficient. So any person who has very less knowledge about the energy or the grade of energy, can easily judge from here that RO process is efficient, because it can only see the figures, that is 3.5 as compared to 61 plus 1.5 and 72 to 2.5. So in other words, he is comparing dollar with dollar. Electricity with thermal, according to him, is the same energy levels. So he can compare, because he's thinking that the dollar is same, the US dollar is same as Australian dollar. But before comparing like this kind of the comparison, dollar with dollar, we have to be careful that these dollars have the different values. The US dollar is not same as Australian dollar. So in other words, electricity is not same as a thermal energy. So from here, we cannot simply say that the thermal process, the RO process are efficient just on the basis of the numbers. So we have to see carefully that one US dollar it has a conversion factor with the Australian dollar. They are not the same in value. So in other words, the electricity is not same as a thermal energy, is not same as a primary fuel energy, and is not same as a standard primary fuel energy. So this is very important to understand that all the energies are at different at grades, and they have the different values, and it must be deal accordingly. We cannot just compare with the values with the numbers. So in other words, that just on the basis of these numbers, we cannot compare RO process with the thermal process, because the energy grades are different. We cannot compare electricity with thermal energy. So we have to find out some common platform where we can convert all the energies to that common platform. Then we can compare all the desalination process. But over here we can compare RO with RO and the thermal with thermal. That comparison will be correct. But the cross comparison from one technology to another technology, it must be done on the common platform. That is actually the main idea of this webinar. So we developed the standard primary energy concept, and this concept, we actually proposed that all the energies are actually produced at adiabatic flame temperature, at the combustion chamber temperature. So all the process must be compared from adiabatic flame temperature to the lowest temperature, that is the ambient condition, where all the heat is actually rejected to the ambient to complete the cycle of thermodynamics. So all the process must be compared at the adiabatic flame temperature to the lowest temperature. So the process can operate in between these two limits, but they must be bring to the same level, bring to the adiabatic flame temperature limit to compare at the common platform. So let's say we showed over here two process, and we converted it into the heat engines work, and then we find out that what energy is actually equivalent energy is consumed if we compare it at the adiabatic flame temperature. And on this basis, then we develop the standard universal performance ratio. And we can see over here in a conventional system, there's only equivalent heat of evaporation divided by energy, where they add up all the energies, electricity and the thermal. That is actually not the correct approach, because we cannot add simply electricity with thermal, because the grades are different. So we introduce over here the conversion factors. Those conversion factors will help to convert all the energies back to the primary energy, and then we can add up all the energies, because they are at the common platform, they are all at the primary energy. And on this basis, then we can compare all the desalination technologies irrespective of the used input energy utilization. We can compare on the common platform. So to do this one, we considered a real practical case. We can see in the real system, normally it's a combined cycle power plant, where there's a gas turbine cycle, and then there's a steam turbine cycle, and then there's a desalination cycle. So this desalination cycle, it can be thermal system or it can be RO system. So initially, the fuel is supplied to the combustion chamber, and where initially the electricity is produced in the gas turbine, and the exhaust of the gas turbine is recovered in a heat recovery steam generator to produce the steam. And this steam is actually supplied to the gas turbine cycle. So this, it can be a three stages steam turbine: high pressure, medium pressure, and the low pressure. It can be a one stage steam turbine depending upon the power requirement. And if it is a thermal desalination system, normally the steam is bleed from the last stages of the low pressure turbine, and then it's supplied to the thermal desalination system. If it's the RO system, then actually RO system is don't have the synergy with CCGT power plant, because the RO system, it no need to be with power plant because it utilizes directly the electricity from the grid. But the integration of the thermal system with the power plant, it has a very good synergy, because if we look into the carefully, that the steam that is bleed from the last stages of the turbine is actually already performed most of the job. So this is almost a dead steam. So just before going to the condenser, where it will be condensed in the condenser, it is extracted and it is utilized in the desalination cycle. So desalination cycle, thermal desalination with power plant has the best thermodynamic synergy, because they are designed to operate at that condition. Steam turbine is designed to operate at high temperature and pressure, and the desalination cycle is designed to operate at low pressure and the low temperature. So they have the best synergy and the best utilization of the available energy of the primary fuel. So we did the complete analysis, and we compared our proposed methodology with the conventional energy approach. So conventionally, the people use the energetic approach. So the main problem with the energetic approach is that it cannot distinguish the different grades or the quality of the working stream, because it's mainly based on the flow rate. And as I mentioned, that the steam that is bleed from the last stages of the turbine, its quality is totally different than the high pressure steam that is supplied to the first stage of the turbine. So if we just consider the flow rate, then it will be like we are penalizing the thermal desalination system, and that's not a correct and a fair comparison. The analysis. So that is the main problem, and we can see that if we apply the conventional energy approach, it shows that the gas turbine consume around 40 or 43% of the input fuel exergy, steam turbine is around 40%, and the desalination is around 16% of the input fuel exergy. But if we apply the fair and the correct exergy approach, the exergetic analysis is the only analysis that can capture the quality or the grade of the working stream utilized by the different process. So we can successfully capture the exergy of the working stream or the quality of the working stream utilized by the each turbine and the desalination process, and we can see the figures are totally different. So if we apply the exergy approach, we can see the gas turbine consume around 58%, and steam turbine is around 38%, and the desalination is only 2.8%. So this shows that in the industry, currently they are actually penalizing the thermal desalination process by overcharging up to 16% as compared to 2%. So this is the main point, that normally they show that the thermal desalination process are not very efficient. Actually, the economic analysis that is applied in the conventional system is not fair, it's not correct. So based on this, the proportions of the primary fuel utilized, we developed the conversion factors. So we showed that for this CCGT power plant, the conversion factor is around 49% or 49.7% for electricity to the primary energy, primary energy to the electricity. So in other words, the CCGT power plant efficiency is around 49.7%. So it shows that to produce 1 unit of the electricity, we need around 2 units of primary fuel energy, because the power plant efficiency is around 50%. And similarly, we converted the thermal energy into the primary fuel energy, and we showed that the conversion factor is around 35. It shows that the 1 unit of the primary fuel, it can produce 35 units of steam at that grade. In other words, by consuming the 1 unit of the primary fuel, we can produce 35 units of that low grade steam that is required to run the thermal desalination process. So now we develop the conversion factors where we can convert the electricity into primary energy and the thermal energy into the primary energy. And by converting this one, then we can add up and we can compare the process. We can see over here again, these are the electricity. These are the three processes again, SWRO, MED, and MSF. And these are the electricity consumptions. And these are the thermal energy consumption by the process. And these are the the conversion factor that just now I explained. So by using these conversion factors, we can successfully convert the electricity into primary energy and the thermal energy into primary energy. And by adding up, we can see over here the primary energy factors now. So we can see RO is actually consumed 7.04 kilowatt hour standard primary energy per cubic meter, while MED is 4.7 and MSF is 7.43. So now you can see from here very clearly that which process is more efficient, because this standard primary energy is a common platform where we converted all the energies to the standard primary energy, and we can compare fairly and accurately. And we also try to find out that what is the standard universal performance ratio. And this standard universal performance ratio we calculated, and it showed the performance ratio for SWRO is 91, and MAD is 135, and MSF is 86. But what does these numbers shows? Is it efficient? Is it not efficient? Or slightly efficient? Because if we just look into the number, these are just numbers. So to find out this answer, whether it's efficient or not efficient, we went back to the thermodynamic limit. So thermodynamic limit that control the separation process, and for irrespective of process, the thermodynamic limit, the minimum energy required for separation is around 0.78 kilowatt hour per cubic meter at 35,000 ppm at 30 degrees centigrade, irrespective of the process, because it's a thermodynamic limit. So if we use the thermodynamic limit, we can find out the thermodynamic limit for the performance ratio, and that number is 828. So it means that theoretically system should achieve 828 at thermodynamic limit, but of course practically it's not possible. But we can compare these numbers to find out the percentage of the performance. So if we compare these numbers with 828 thermodynamic limit performance ratio, we can see over here, it's very interesting to see that all the processes are actually operating from 10 to 17% of thermodynamic limit. So as I showed earlier, that the both group, even SWRO or the thermal process, they claim they are very efficient, but unfortunately, both processes are not efficient. We are only operating 17% or 16.4% maximum to the thermodynamic limit, and there is a huge gap available for the development to improve the process efficiency of the process. And of course, with these numbers of the percentage of thermodynamic limit, all the conventional processes are not sustainable for the future water production. And then we try to find out, we applied the same our methodology to over 60 plants from all over the world. And it was very interesting to see that actually the horizontal axis shows the years. We started from 1980s when the desalination commercially was started until today. And the vertical axis shows the standard universal performance ratio and as well as the percentage of thermodynamic limit. So in terms of the percentage of thermodynamic limit, we can see from 1980s until today, there's no much change in the performance. Even in the UPR, SUPR, we can see there's a slightly change. And we are only operating from 10 to 13 or 16% of thermodynamic limit. But the future sustainability is actually if we achieve 25 to 28% of thermodynamic limit. That is around 250 standard universal performance ratio. So we are very far from future sustainability, and we have to develop, or we have to find out of-box solutions to achieve this sustainable zone for the future water supplies. So as I mentioned earlier, that thermal desalination process are very they are employed more than 60% in GCC countries. So we started work on a multi-effect desalination system, because multi-effect desalination system is the most efficient system, as just now I presented. And we try to find out that how we can improve the efficiency or the performance of the system. So actually, in multi-effect desalination system, let me explain a little bit about the process. The steam, the heat source is supplied. These are actually the heat exchangers. Those are arranged in a series manner. So heat is supplied to the tube side of the first effect, and the seawater is sprayed on the outside of the tube. And the vapor produced over here is actually going to the tube side of the next effect, and where this heat of the condensation is utilized to evaporate another feed on the outside of the tube, and then the vapor is going to the next stage. So we can see over here the heat is supplied to the first effect only, and then the vapor produced in that effect is actually the energy is recovered in the successive stages. So in other words, it shows that the efficiency or the performance of the system is depend how many number of the recoveries we have in the system, because the heat is only supplied at once, and then there are the recoveries that actually dictate the performance or control the performance of the system. So it means if we have more number of recoveries, the performance will be high. If we have a less number of recoveries, the performance will be poor. In conventional system, we can see that it operates from 70 degree to 40 degree centigrade, and it normally it don't operate above 70 degree. The reason, because it's controlled by the fouling and the corrosion element in the seawater, and it cannot go beyond 40 degree centigrade because it's controlled by the ambient condition. So because of this limited operation range, there are the limited number of the recoveries from 8 to 10. That's why the performance is limited of the conventional MED process. So this shows that we can improve the process in two ways. The first is if we are able to overcome this top temperature by somehow we control the corrosion and the fouling, and we improve the temperature to over 100 or 120 degrees centigrade, and we operate from 120 to 40 degree, it will help to improve the process efficiency, because we can insert more number of recoveries. And the second one is if we are able to overcome the ambient condition limitation, and we can drop the temperature to below ambient condition, then again we can improve the number of recoveries and the performance will improve. So it means these are the two ways that we can improve the performance. So this shows the same thing, that the operation, the controlled by the scaling and the temperature limits by the MED and MSF. Otherwise, there will be a scaling on the tube surfaces. And over here it shows that the number of the recoveries can be 6 to 8 from 70 to 40 degrees centigrade. And we started work on the lower brine temperature, and we proposed our innovative adsorption cycle, that if we integrate the innovative adsorption cycle to the last stage of MED, we can actually overcome the last stage temperature. So over here, what we are doing, we are actually disintegrating the condenser from the last stage of the MED. So from the last stage of the MED, the vapors are going to our adsorption cycle, the adsorption bed, and where it can pull the water vapor from the last effect, and then it can dissolve into the condenser. So we can see over here, there's no direct link between the condenser and the last stage of MED. There's an in between is the adsorption cycle that help to overcome the ambient condition at the low brine temperature limitation. By doing this one, we can operate as low as 5 degrees centigrade, the last stage. So it means from 70 to 5 degree, we can actually install more than 15 number of recoveries as compared to 8 and 10 the conventionally. So in other words, it will boost the water production to almost 2 times. And secondly, we also thought about that how we can improve the top brine temperature. So there is a solution, and we come up with the solution that if we remove the soft scaling component from the feed, in other words, we do the pre-treatment with the nanofiltration, or we use the scale inhibitor like an anti-scalant, we can actually increase the turbine temperature to 125. So by operating from 125 to all the way 5 degrees centigrade with more than 20 number of recoveries will be the best cycle in the world to operate for the desalination process. So this was our target, and to achieve this target, we started the investigation, the pilot scales. But before going to the piloting, I would like to explain the operation of the adsorption cycle that we introduced. So adsorption cycle is actually adsorbent beds, and these are the two adsorbent bed where we pack the silica gel adsorbent in the form of the cakes. So why we use the silica gel? Because firstly, the silica gel is very cheap, and the secondly is available freely all over the world. It's not controlled by one company or by one country. It's actually abundant, available easily, and secondly, it's very stable. There are the many other materials nowadays in the market, like metal organic framework or the other materials. Those firstly are very expensive. They cannot be produced in a mass production, and the secondly, they're not very stable for over the life period. So for the silica gel, it's very stable, and it's very efficient also in terms of the water absorption. And how it work actually? So actually, this is the last stage of the med, and firstly, this bed is undergoing adsorption cycle, so the wall will open and the vapor will be adsorbed on the silica gel surface. So because the silica gel is a fixed amount, so after some time it will be fully saturated, it cannot take more vapors. So what will happen? This valve will close and the adsorption will start on the other cycle. So we can see over here, once it will be fully saturated, it cannot take more vapors and the valve will close. So now you can see it's a switching. So this valve will be closed and this valve will be open, and the vapor will start adsorbing on this bed. At the same time, we supplied the heat source from 60 to 85 degrees centigrade to regenerate this silica gel to prepare it for the next operation. And the desorbed vapor are going to the condenser. Because the silica gel has a very high affinity for the water vapor, so that's why it can reduce the pressure and the saturation temperature to as low as 5 degrees centigrade of the last stage of med. And this how it work. And this batch operation, the size of the silica gel and the beds is depend on the size of the med system, and there's no scalability issues because it can be in the form of the big silos, and the silica gel can be dumped into the big silos for the adsorption and the desorption process. And interestingly, if we see over here, the most of the parts are actually stationary, and there's no moving part. So its system required very less maintenance, or except only the valves that is actually opening and closing. And the silica gel is also stationary, and this is a physiosorption process, not a chemisorption. So it's very stable and very reliable system. So this is how we integrated. We can see these are the med stages. In conventional system, the vapor from the last stage is actually going to the condenser. And in our hybrid system, the vapor from the last effect is going to the adsorption cycle, and then we supply the desorption heat, and it dissolves and condense in the condenser. So we actually bypass the condenser, and we introduce the adsorption cycle in between the med and the condenser. So this is a 3D model how it look like. So we can see these are the med stages, the pipe linking from the last stage to the beds, and there are some utilities to operate the system. So this is our control of our med system that we installed over here in KAUST. So we can see over here that we have the 4 effect med. This is the first effect, second effect, third effect, fourth effect, and the last condenser. So this seawater is coming from the sea, and it passed through the last condenser, and then the part of it is supplied parallel to all the effects. At the same time, we have the small boiler to supply the heat source to the first effect, and the vapors are cascaded to the successive stages. So in conventional system, this last stage temperature is controlled by the seawater temperature. Now we can see over here around 41 degrees centigrade. But in our hybrid system, we bypass this condenser and the vapors are going to the adsorption cycle. So this is how we hybridize med with the ad cycle. So this is our pilot over here in KAUST. So we can see over here, this is the adsorption cycle pilot. And these, because the absorption cycle is operated with the solar, so we have the hot water storage tanks over here. On top of this one, we have the platform, and we install the MED that can be seen here. So the AD's pilot is actually below this platform, and these two big pipes actually are integrating the last stage of MED to the absorption cycle to run it as a MED-AD hybrid cycle. These are the solar collectors. Those are installed on the rooftop and 352 meter square area to operate the absorption cycle from 60 to 85 degrees centigrade throughout the day. So we operated our system for 1 week continuously, because a pilot, as an industrial pilot, normally 1 hour or 2 hour experiments are not appreciable by the industry. So we can see over here for 3 days we operated as a conventional MED, and for another 3 days we link it to the AD, and we operated for the whole week to check the stability of the system. So we operated at 50 degrees centigrade heat source. In terms of conventional MED, we can see over here the last stage temperature was 40 degrees centigrade. That is very close to our design, because the conventional system normally they operate 2 to 3 degree interstage or inter-effect delta T, with the last effect at 40 degree when the seawater is around 32 to 33 degrees centigrade. So after 3 days successful operation of the MED, this was the point where we open the valve to link it to the absorption cycle, and we bypass the condenser. So we can see over here the interesting phenomena happened. The absorption cycle successfully pulled down the temperature of all the stages, and we can see over here the last stage was operating at 25 degree when the feed water was at 33 degrees centigrade. So this was the first time in the history of the desalination that the MED was operated below the ambient condition, and we successfully operated it over here in the pilot. And this 25 degrees centigrade is controlled by the hardware, because we have only 4 number of the effect. It's a research facility. So it shows that there is a gap available over here to insert more number of effect. Or in other words, we can reduce this heat source temperature to around 40 degree to operate last stage at around 7 to 10 degrees centigrade. So in either way, if we keep the heat source temperature same, we can see the inter effect. The temperature was almost 2 times as compared to the conventional MED system, from 2 to 3 to 5 to 6 degrees centigrade. In the greenfield design, we can increase the number of the stages to like 15 to 18 number of the stages. So here are the water production. Interestingly, we can see over here the water production in terms of the conventional MED, it was around 2 liter per minute. But when we hybridize it with the AD, the water production was boosted to 4 liter per minute. So we can see very clearly, by keeping all the operational parameters same, the water production was boosted to 2 times as compared to the conventional MED with the integration of the AD cycle. That was successful demonstration of our hybrid cycle. And then we operated our system for all the temperature range to show the operability at all the temperatures, heat source temperatures. So this green line, it shows the liter per minute water production of conventional MED system, and this red line, it shows the water production of our hybrid system. So we can see at all the temperature range, our hybrid system water production is more than 2 times as compared to the conventional MED system. On top of that, the conventional MED system, the temperature limit is around 38, but we can go as low as 15 degrees of heat source. The last stage is operating at 5 degrees centigrade. So this was a successful demonstration of operationability of our hybrid system below ambient condition, but still producing almost 2 times higher than the conventional MED system. So after this successful demonstration of the lower brine temperature limit below the ambient condition, we started work on the top brine temperature, that how we can push the limit to over 100 degrees centigrade. So before that, we have to look into the chemistry of the seawater. So we can see over here that in the seawater, we have the cations, we have the anions, and that actually form soft scale and the hard scale in the system at specific temperature and the concentration. So if we want to operate the MED system at high temperature, we have to overcome the soft scaling and the hard scaling component to operate successfully at high temperature. So this shows that the operability of the conventional system. So this is the concentration. Normally is a 38 to 40% recovery, and this is the temperature. So this is the conventional operation of the MED system. So we can see normally they operate around 60 to 65 degree with 50% recovery. So it's operating away from the hard scale, that is a calcium sulfate or the gypsum hard scale zone. It sometimes it forms soft scale that can be easily washed by the seawater spray. But if we want to operate the system at 120 degree as we propose with the same recovery, actually we are in the hard scale zone. So it means we have to remove this element from the seawater before introducing into the system to prevent the hard scale formation on the tube surfaces. So what are the solutions? We propose two solutions. One is a nanofiltration for the pre-treatment, and other is we can also add anti-scalant to inhibit the scale formation. So we did the experiments, especially the nanofiltration we did with the collaboration of the SWIC, and we successfully showed that all the scale, the dissolved salts, after the nanofiltration, it can be removed until the point that there will be no hard scale formation. And after 6-month trials, we open up the heat exchanger and it shows that there's no hard scale formation. This white powder is a soft scale formation that can be easily washed with the spray of the feed. We also tested the anti-scalant that we got from the Dow and the Nalco, and we successfully showed at the different concentration of the anti-scalant how much the scale formation can be removed. So this is the baseline test, so we can see how much the scale formation was, and with the 1 ppm dosage, with 2 ppm and 4 ppm, we can see it was very successful to overcome the scale formation on the tube surface. So we showed that either nanofiltration or the anti-scalant are the two solutions that can help to improve the temperature of the MED to over 100 degrees centigrade successfully. So to investigate the performance of the system, we did the simulation. So we can see over here, if we operate the system at 95 degrees centigrade heat source until 5 degree, we can typically install 24 number of effects as compared to 6 or 8 number of effects in the conventionally. So by doing this one, we can improve the water production. And if we go back to the same chart again, where I showed the performance of all the three conventional system, if we compare our system, proposed system, hybrid system, NF with MED and AD, we can see we can achieve 17% as compared to the 13 or 14% of the best available system of MED. So we improved the performance until 17% by hybridization of the process. So if we revisit the chart again, the trend of the UPR, so we can see over here that we were able to achieve 17% of thermodynamic limit, but still we are not into the zone of the future sustainability, and we are almost reaching to the sustainability zone. Since we are operated with from 95 to 5 degrees centigrade, so we achieve 17%, and we hope and we are quite confident that if we operate the NF, MED, and AD from 125 to all the way 5 degrees centigrade, we can easily achieve around 22 to 23% of thermodynamic limit that is in the sustainable zone, and that will be the best cycle that will be available in the market today. We also did the cost comparison, the life cycle costing, because as I mentioned, it's very important to achieve the energy, water, and environment nexus. On top of that, it must be the cost efficient. And we showed over here that the first bar for all the process is the conventional energetic approach, and the second bar is our exergy analysis. And we showed that all the conventional process, out of all the process, our process is the lowest water production cost, that is around $0.48 per cubic meter, as compared to RO that is around $1 per cubic meter, and the MED that is around $0.9 $0.98 per cubic meter. So our system is the best system available today in the market that can produce the water with less than $0.5 per cubic meter. So now the question is that even we hybridize the system, and as I showed earlier that from 1980s until today there was a marginal improvement in the performance. So how we can get the high jump in the performance? So to find out this one, we went to the history again, that we can investigate how the previously the major improvements was done. So the desalination was started in 1500th century on the ships, and when the performance ratio was less than 1, because it was an open pan where they burn the fuel and the water was evaporated, the performance was very low. And then there was a jump in the performance when the boiler process was came into the market, because the fuel can burn very efficiently, and there was a performance improvement. And then there was another jump in the performance when the multi-effect desalination and the multi-stage flashing came into the market, because they can reutilize the vapor many times. And then there was another jump when it was integrated with the power plant for the best thermodynamic synergy. And after that, we can see over here again the same chart, there's no improvement at all, there's only the marginal improvement. So what lesson we can learn from here? That we can learn the lesson that without changing the technology we cannot get the high performance improvement in the process. In other words, with improving the material or with improvement of the process, it can be only marginal change in the performance, as we can see since 1980s. But if we don't change the technology, we cannot get the high performance jump. So we are now at the verge of the point where we need to change the technologies. We need to come up the out-of-box solutions to get another jump to achieve the sustainable desalination zone. So this what lesson we learned from the past. Even we do the material development or the process improvement, we will be not able to achieve the sustainable zone until we do the some technology change or out-of-box solution. And our hybrid system that we achieved around 22% of thermodynamic limit is one of the example that showed that by integration of the technologies to overcome the limitation of the conventional system can help to achieve the sustainable zone. Then we revisited all the technologies and we try to find out that what are the hybridizations are possible, and then we rank the different technologies. And we can see over here, these are the three conventional technologies. It can be NF with MED, it can be NF, MED, and AD. It can be RO process with MED, RO process with MSF, or it can be NF, SWRO, MED. And we calculated the primary energy and the performance, and we also calculated the percentage of thermodynamic limit for all the process. And interestingly, we can see over here in the ranking, again, our system, NF, MED, and AD, was the highest performance process as compared to all available process. And the second one was if we integrate SWRO with MED for more recovery. And similarly, the other process. But interestingly, we can see over here the SWRO process that most of people claim is most efficient is actually ranked at 6. It's not very efficient. But again, the main point is if we check into the thermodynamic limit, all the processes are still operating maximum 17% of thermodynamic limit. So it means all the processes are actually not very efficient. So we have to work hard to find out the most efficient solutions or the out-of-box solutions to achieve the sustainability zone that is around 25 to 28% of thermodynamic limit. So with this one, I will conclude with a few words that the hybrid desalination process is actually the way forward, as we can see, to overcome the conventional system limitations. And to overcome the top brine temperature limitation, it can be anti-scalant or the nanofiltration, and we can successfully improve the top brine temperature to 125 degrees centigrade. And our proposed tri-hybrid system is the best cycle that can achieve the future sustainability goal, 17% of thermodynamic limit. And our technology also won the award because our technology is the only one technology in the world that can produce the water less than $0.5 per cubic meter. And we won the GE Aramco Global Innovation Award out of 150 applications as the best technology available today in the market. And we were also highlighted on the Nature and on the Yahoo Business as a successful technology transferred into the market. We have the pilots. We have one pilot in the National University of Singapore that is around 3 cubic meter per day capacity, MEDAD hybrid pilot. And we have another pilot that just now I showed at Cows that is 10 cubic meter per day operated with the solar. And we are not only in the lab, we successfully commercialized our system to the industry. And we last year in February we inaugurated our first plant at Cox Solar Village, King Abdulaziz City of Science and Technology in Riyadh. And it was inaugurated by the Minister of Petroleum, and it's operating successfully. And after the successful operation of this plant, we got contract of another plant that will be installed at Jambu in Saudi Arabia. The capacity is around 3,000 to 5,000 cubic meter per day, depending on the waste heat available. And we almost finished the design, and now we are in the fabrication state. With this one, thank you very much.
Okay, thank you, Dr. Wakil. That was a really interesting presentation, and I appreciate you taking the time to explain that all to us. We had a few questions come in while you were giving your presentation, and so if you don't mind taking a few moments to answer some of these questions, that'd be really great.
Sure. Yeah.
One of the first questions was, what is the standard universal performance ratio of conventional distillation?
So actually, firstly, we need to understand what is the standard universal performance ratio. So standard universal performance ratio is based on a standard primary energy. In other words, it equalizes all the energies at the adiabatic flame temperature. So we have to convert all the energies to the equivalent adiabatic flame temperature energy. And then this conversion factor will help us to convert all the grade of energies, either it's electricity, either it's a steam at different temperature and pressure, to that common platform, and then we can add up all these. So if we do this one with the proper exegetic analysis, we can see that the standard universal performance ratio of the conventional system is only less than 18% of thermodynamic limit. So technically or thermodynamically, the thermodynamic system can easily achieve 30 to 35% of efficiency as IC engines are operating. So if we look into that manner, we are very low and we are not efficient at all. And the whole world claim that their process is efficient, but unfortunately we are not efficient. We are way far from the efficiency. It's only 17% of thermodynamic limit. So we have to improve the process to achieve the highest efficiency. And the sustainability we can only get if we achieve around 25 to 28% of thermodynamic limit. And that is a bit realistic and we can easily achieve. It's not like not achievable goal. It's easily can be achieved.
What do you think are the driving forces behind those who claim currently that the processes are energy efficient? I mean, you mentioned at the start you had one camp talking that RO is the way of the future and it's very efficient. On the other hand, you've got the other camp who's talking about thermal processes. Where's the driving forces coming?
So actually, the driving force is the economics, because we know that all the countries are developing very fast. So as I mentioned, the UN limit for the water is 1,000 cubic meter per capita per day. So it means if the water in any country is less than this limit, the water is just enough for the survival. It's not available for the development. But if we look into the development, it starts from the daily life cycle to the industry, to the plants, to the agriculture. Everywhere you need the water for the life cycle. So these are the major drivers that actually pushing the desalination industry to produce more water. And the desalination industry, without caring the energy, They are just installing the same process again and again because they are very comfortable. So they don't want to come out from the comfortable zone. So this is very important at the government level also. They have to put the restrictions to for the each plant, for the every plant that will be installed in the future must achieve some efficiency level. Otherwise, it will be very difficult to come out from the comfortable zone that is recently going on.
Okay. We had a few questions also come in from some of our listeners.
Sure.
I'll try and relate them to you. So the first question was regarding the correction factor, which is from the exegetic analysis, where we say that 35.33 units means essentially 1 unit of primary energy, but MED takes 61 kilowatt hours per cubic meter of low-grade thermal energy.
Sure.
With low-grade energy, if we produce electricity instead of MED, it can be around 6 kilowatt hours per cubic meter, and equivalent primary energy will be more. But the proposed correction factor gives a very low figure of around 1.7 kilowatt hours per cubic meter, and this wasn't to be understood by one of our listeners.
No, because firstly, the CF is the conversion factor. So this conversion factor is not a universal. It's totally depend on the temperature and the pressure condition of the steam that is bleed from the turbine state. So if we bleed the turbine of this steam from the middle turbine, intermediate turbine, this conversion factor will be lower. It will be not 35. So we are bleeding at 70 degrees centigrade. At that condition, the conversion factor to the standard primary energy is 35. So in other words, it doesn't mean that if you install a separate boiler to produce this energy, you will get this conversion factor. This is not true. This is only true for the CCGT plants. So what I mean that we are comparing the today's best available technology. So when we are comparing the different technologies, we have to consider the best available technologies in the market. So the best available technology is the CCGT power plant with desalination. So that will be the correct analysis. If we compare the boiler operated with MED, boiler operated MSF with RO, or only the steam turbine with thermal with RO, that will be not a fair comparison. So we have to consider the best available practice CCGT plant that is the highest efficiency over 50% in the market to compare all the process. And the second point that just now you mentioned that if we pass the steam to the turbine and we produce the electricity, is it okay to operate the RO or we bleed the steam to run the MED? So this is a very good question, and most of the people they claim that if we don't bleed the steam and let it pass through the turbine, we can generate the electricity and we can run the RO plant. But the exegetic analysis showed that the electricity produced by that bleed steam is not that much. You have to extract more energy to produce the same amount of the water if you run the RO plant. But if you extract the steam and you run the MED or thermal desalination process, you can produce more water. So it shows that by bleeding the steam from the last stages of the turbine is more efficient as compared to by producing the electricity and running the RO plant. But if you do the conventional energetic analysis, then the results will be different. That is not the fair analysis.
Okay.
Yeah.
Good explanation. Okay. And then the following question came up and said that for the combined process, the MED-AD process, the large stage can go up to 5 degrees Celsius, but the specific volume of vapors will be high, and vacuum is also high, so we need a larger size and thicker shell. Will this affect the capex of the overall capex of the plant?
This is a very interesting question. So actually, before doing this one, we did another experiment to show this thing that at lower temperature, below 40 degrees centigrade, is actually heat transfer coefficient is also very high. So if you read through some literature, you will find that below 35 degrees centigrade, where the specific volume is very high, the heat transfer coefficient is almost more than double. So it shows that if the heat transfer coefficient at that temperature is double, actually the same area will be more than enough to condense that big amount of the vapors, because the heat transfer coefficient is also doubling. So that was a successful demonstration to show that even we lower the temperature, the specific volume is increasing, but on the other hand, the overall heat transfer coefficient is also increasing. So the condensation will also be improved. So you don't need a big area to overcome this, the big volume of the vapors. It will be handled by the heat transfer coefficient automatically.
Very good. I guess following on from that, as engineers, we're always trying to find the most cost-effective solution, right? So we're trying to find an optimization of OPEX and CAPEX, and with any process,
Sure.
the slower the process goes, the more efficient it is, from an OPEX perspective or from an energy efficient perspective. But that means a much bigger CAPEX, a much bigger installation, bigger plants. How do
Sure.
you go about trying to find that optimum point between these things in your process or just in general?
So we actually, it's not like only we showed that the water production is double. As I mentioned, that the cost is also a major factor, because we cannot promote a technology where the water production cost is very high and the people cannot afford. So the technology should be efficient, but on top of that, the water production, the cost must be reasonable. So that's why we did the life cycle costing. So this life cycle costing is not just a energy; it's a capital cost with the lifespan of the desalination process. So the costing that I showed, $0.5 per cubic meter, it include the capital cost, and it include all the operational cost and the maintenance cost. So it cover all the aspects of the process that is actually essential for the operation and the installation. So it showed that our technology is the most efficient as compared to all the available technologies in the market.
Okay. I want to touch on that a little bit as well. For your cost estimation, were you just looking at the desalination process itself in terms of removal of salts from seawater, or did you take into account all the intake systems that needed to be in place, the pump stations for the intakes, the post treatment, the dealing with any brines or backwash waters from the process? So, did you look at a full process design and costing, or just focus on the desalination for your costing?
No, actually, in all the desalination process, when we compare the costing, it's actually from plant intake to plant inlet to the plant outlet. So it means when the seawater is entering into the plant, it include all the pre-treatment facility, the main treatment facility, and the post-treatment facility, and at the point until it leave the plant. So that is actually we consider for all the technologies. So it's quite fair that all the technologies, the intake facility that is off before the plant is not considered. So it's not considered for all the technologies, and all the pre-treatment and the post-treatment are included in the life cycle costing.
Very good. And maybe you've probably seen, a lot of the tenders recently. I think the bids that have gone in recently for the Tavila combined RWPP plant and Rubik 3, they're all sitting for their build own operate costs of around $0.5 US dollars per cubic meter. So sort of in this range as well. Does that mean that they've made some developments in fields of seawater, RO, and so forth, or how can these costs reduction in the last few years be explained, do you think?
Actually, this because it's also depend on we need to look exactly the cost means, because if the plant is installed with the existing facilities, so they use the existing facilities for their plant, so that cost is not actually included. So we have to look for the total cost of the plant. So let's say if Tavila is already there's a plant are operating, so if they are using the facilities to operate the new plant also, just by improving a little bit with the existing facility, of course they can reduce the cost of the operation of that plant. But if the new plant is installed at that cost, it means it should be some hybridization or some hybrid process, because the individual process is controlled by the limitation. So as I showed that with the existing process and with the existing material, it's not possible to improve more than 13% of thermodynamic limit, whatever you do, because it's controlled by thermodynamics, and we cannot do with thermodynamics unless you improve the technology or you bring some very efficient material like a graphene. But the graphene is still at the lab scale. You cannot see any pilot in the real market. So that can be a breakthrough. that can bring a very like efficient process, but it will take time. On the other hand, the thermal process, they are integrating MSF with MED, NF with MED, or MED with AD. Those all are the available technologies in the market, and those are very like a successful technologies and available in the shelf to operate. So those can be like a near future solution to achieve the sustainability. But for the long term, we have to develop the graphene or the other innovative material to get the high sustainability performance.
Very good. We had one more question come in from one of our viewers. It's regarding the silica gel that's used. So the vapors that absorb in the silica gel bed and then desorb, are there any chance that the silica gel will form contamination in the distillate?
So firstly, its name is silica gel, but actually it's a beads. It's a like 1 to 2 millimeter diameter. The silica bead is actually a sand, very fine sand. So you can only get the contamination if there's a chemical absorption process. So this silica gel adsorption is a physiosorption. So it's physically stick to the silica gel surface, but there's no chemical process going on. So technically and theoretically, there is no chances of the contamination because the vapor just stick to the surface and then leave the surface, and this is a pure sand. And on top of that, the repeatability of the cycle is actually we are running our pilot more than like 18 years, and we didn't change the charge of silica gel. So technically, it can go more than 30 years with the same charge of silica gel. So you don't need to change the silica gel because it's just packed in the bed and there's no movement in the silica gel. It's just a water vapor is adsorbed and the water vapor dissolved from the silica gel.
Very good. Okay. Just to wrap up, there was a quick question to find out when's your next conference?
Oh, I'm going to this. There is one conference in Indonesia, and then there is another conference in Abu Dhabi. That is on the renewable energy. So I will be presenting over there. Yeah.
Very good, very good. And there was another question came in asking if this project can be run in Pakistan with the support of KAUST. Maybe I'll leave you to contact the questionee yourself to chase that one up. So on that note, I want to thank you very much again for an extremely interesting presentation. I think everyone's thoroughly enjoyed it. Found it's very, very fascinating and been able to open our minds on the concept of energy efficiency and what it means. And obviously we're all working on the same targets to bring down the cost of desalination and look for sustainable water supplies and sustainability heading forward. So really appreciate all your work you're doing in this and your work on the YLP committee as well. And so thank you very much. I'll leave you to say goodbye to everyone and we'll wrap up.
Yeah. Thank you very much, everyone, for listening and watching this webinar. And I hope it will be beneficial for all, because this is a very hot topic nowadays. And of course, we all need the water. And I hope the message that I try to convey that the technology must be compared at the common platform, not on the individual technology energy basis. And we have to be careful when anyone claim that the technology is very efficient. We have to be careful for the energy grade of the energies. So with this one, yeah, thank you very much.